Okay, so as rich, I'm going to start with the probability density function of a normal random variable. So this is the function that is plotted on the right over there. And just as a reminder, a PDF is a function that is positive and that integrates to 1. And if you want the probability for a draw of the random variable to be in a given interval, then you just need to integrate this function over the interval you're looking at. And if you look at the more mathematically, the way this PDF writes, so it is the exponent of something that is quadratic. We don't have to worry too much about the factor that is in front here, because this factor just ensures that this function integrates to 1. And if we look at the parameter of a univariate normal random variable, there are 2 parameters, the mean mu that correspond to the expectation of the variable, and the variance sigma square, that is the variance of the random variable. The mean can be any real value, and the variance has to be a positive number. So now if we move to multivariate random variable, so we say that the vector follows a multivariate normal distribution if a linear combination of this vector is a random variable that is normally distributed. So this is basically what is written here. So whatever the coefficients alpha that I pick, if I make the product alpha transpose times y, so alpha is a vector and y is a vector of the random variables, then this gives me a univariate random variable that has to be normally distributed. This is the definition of a multivariate normal distribution. You have 2 examples here on the left of samples from multivariate normal distribution, and an example on the right that is a counterexample. This is not normally distributed. If you look at the distribution of y1, it will be normally distributed. The distribution of y2 will be normally distributed if we just look at the variables independently. But the joint distribution of the 2 of them is not normally distributed. If we look at the contour line of the density of these points, we can see it's not an ellipsoid. So the PDF for multivariate Gaussian is just the generalization of what we've seen in the univariate case. So it's the exponent of something that is quadratic. The only difference with before is that x in this expression is now multidimensional. It's not a scalar anymore. And the coefficient is in front here is just a coefficient to make sure that this expression integrates to 1. So similarly to the 1D case, the multivariate normal distribution is parameterized by a mean vector. So it's a vector that has the same dimension as the random vector, and a covariance matrix. Rich already said a lot about the covariance matrix, so I'm not going to go into too much detail. I'm just going to stress the important properties of the covariance matrix. So the first one is that it is symmetric. So sigma ij is equal to sigma ji. So this is because the covariance itself is a symmetric operator. And it is also positive definite. So it means whatever the vector alpha you pick in here, alpha transpose sigma times alpha has to be greater than 0. And if we think about it, this is a very natural property. If I come back to the previous slide, we said that this quantity, alpha transpose y, has to be normally distributed. So this is a random variable, so this has a positive variance. And if you write down the variance of this expression using this formula, you will end up with basically this quantity. So imposing the fact that a covariance matrix has to be positive semi-definite just means that this quantity, which can be interpreted as a variance, has to be positive. All right? Feel free to ask questions during the talk. Willie, if you want to chip in, because you see questions on the chat.
Someone's just asked for a clarification: positive or semi-definite? Just
okay. So
explain the requirement for.
Yes. So depending on the book you're looking at, people will use slightly different wording. I use positive semi-definite just to say that this quantity may be equal to 0, like a variance can be equal to 0. The random variable becomes deterministic, but it can still be seen as a random variable if you want. So I'm saying positive semi-definite just to allow for the fact that this inequality may reach the 0 case. Sometimes people say non-negative, they mean exactly the same thing. Sometimes people just say positive definite just for this, even if they include the equality in there. I hope that answers the question. So now let's look at the conditional distribution of a multivariate random variable. So if we apply Bayes' rule, so if we look at the distribution of y1 given that y2 is equal to a given value, we apply Bayes' rule, and this is just the joint distribution divided by the marginal distribution. And if you write down in the Gaussian case, this joint distribution is going to be something quadratic in y1 and in alpha. The part that depends on alpha can be basically put into the constant in here at the denominator. So we end up with something like a PDF that is the exponent of something quadratic. So we recognize here again a Gaussian distribution or a normal distribution. So another way to look at it is if we look at the two-dimensional PDF and we fix the variable x2 to the value alpha in here, the joint distribution, the conditional distribution will just be a slice in the PDF. And if we look at these slides, we end up with something that has the bell shape of a Gaussian. So this is still a normal PDF up to the constraint that it has to be renormalized to integrate to 1. This is why we have the constant in there. And here's another way to illustrate that in 3D. So the cloud of points you can see in here is a three-dimensional multivariate normal samples. So it's a cloud of samples from a multivariate Gaussian. And if I fix the value on the third axis, so let's say I know that my sample is going to take this value in here, I can look at the conditional distribution in there. So here I've just plotted the contour lines. All right. And this distribution is still going to be normal. Okay, so again, this has been said by Rich, so I'm going to say that quite quickly. But if we look at the distribution of a multivariate vector, so in here both y1 and y2 may be vector themselves. So it will have a mean value and a covariance. And the expression for the conditional distribution is still normally distributed. So y1 given y2 is still normally distributed. And we know analytically what is the conditional mean and the conditional variance. And I'm going to detail these a bit again because we'll use it again and again during the talk. So the conditional mean is the mean for y1 mu1 times, plus a cross covariance times the inverse of a covariance matrix times y2 minus the mean. So basically, we'll just pick the right elements in this matrix and compute the product here, and similar for the denominator. So the conditional variance is the initial variance of y1 minus a covariance times the inverse of the variance of what we observe times the covariance again. So we have analytically the expression of the conditional distribution I was plotting, for example, on this slide here. Okay, so now let's talk about Gaussian process. So Gaussian process is very similar to what we've seen before. So it is an object that will return random things, and just instead of returning a random number or a random vector, it will return random function. So you can think something from a Gaussian process, you can think as throwing a dice, just it's a dice that has an infinite number of faces, and on each faces you'll have one of these little curves that is plotted, and you can throw the dice again and again, and each time it will return a new curve. So the definition of the Gaussian process is that if you take a subset of points in the input space, and if you look at the random vector that you obtain by evaluating the GP at the location you've just picked, then this has to be a multivariate normal. So let me show you that on an example. So those are samples from a Gaussian process. I can pick 2 points in the input space. So here I pick 0 and 0.3. And if I plot for each of these curves, if I pick these 2 values here and I plot them as 1 point in there, I can obtain a cloud of points. And the definition of a Gaussian process is whatever the points I took in here, the cloud of points I obtain in there is going to be Gaussian distributed. So if I move the points away, I'm going to have little correlation between the 2 variables because they are far away. So the process has enough space to wiggle in between. And if I move them very close by, then I obtain points that are very close one to another. And of course, if I evaluate at the same point, I obtain the identity. But this is what we mean when we say that a GP, if you subsample from a GP at different location, you will obtain a multivariate normal distribution. This little thing just shows what happened if you take 2 points in the input space, but you could take much more than 2 points. You could take as many as you want, and then you will obtain a high-dimensional cloud of points that I cannot plot directly. But this high-dimensional cloud of point would still be Gaussian distributed. Any question on that?
There aren't, but
okay. Yeah. I'll keep going. Do interrupt me, Will, if you have at some point. Okay, so before we've seen that the univariate and multivariate Gaussian distribution depending on the mean and a variance or a covariance. And it's the same for a Gaussian process. It will depend on the mean function and a covariance function or the kernel. So the mean function just tells you for a given location X, what is the expected value of the process. And the covariance function tells you what is the covariance between 2 points that you evaluate. So if I come back to this little animation, the mean will just be 0 in this case. What is the expected value of the sample at any point in the space? Here I've picked it to be 0, and the covariance will just be the covariance between these cloud of points. And of course, the covariance between these cloud of points depend on the location of points I pick into the input space. So this is why the covariance is a function of 2 variables. It can be understood as the generalization of a covariance matrix. So covariance matrix has 2 entries, and similarly, a covariance function has 2 input variables. So the mean function can be whatever you want, but the kernel function has to satisfy some properties, and it has to be a positive semi-definite function. Being positive semi-definite, so this is the definition. It means whatever points, whatever number n you pick, then you can get any point in the input space and any vector alpha in real, and this quantity here has to be positive. Again, this is not a very surprising property because we said before that a Gaussian process, if you subsample at some point, you end up with a multivariate normal distribution. And we know that the covariance matrix of a multivariate normal distribution has to be positive definite. And this is exactly the same thing we are repeating in here. Here we are just saying that whatever points you pick in the input space, the covariance matrix has to be positive definite. And this is because the variance has to be positive. So there is nothing, maybe it looks a bit scary when you look at the definition itself, but there's nothing tricky in there. We are just stating again and again that a variance has to be positive. Okay, so proving that a function is positive definite is something that can be a bit difficult. We'll see a few tricks later on during the talk. But a good thing is there are many functions that have already proven to be positive definite. So if you open a book about GPs, you will find lists of covariance functions. A common one being the Maten family in here. Rich has already been talking about them, or Brownian motion, white noise. There's plenty of covariance functions that can be used. When they just depend on the distance between 2 points, we say they are stationary. And another thing we can see in this expression is for all of them, we can put a rescaling factor in front, that is sigma square. This factor is often called the variance, because if we choose in here x equal to y, it means in the exponent, this will be 0, so the exponent is going to be 1. So this just says that k of xx is going to be sigma square. And k of xx is, by definition, the variance of the Gaussian process at the location x. So for all these covariants up to this one, the parameter sigma square can be directly interpreted as the variance of the Gaussian process at any point in the space. For these covariants in there, at least the Brownian, for example, the variance will change depending on when you are into the space. So this parameter cannot directly be interpreted as the variance of the Gaussian process, but it is a variance parameter. And similarly, we have another. So this parameter sigma square rescales kind of vertically the function k. And similarly, we have another parameter that is theta, that always divide x and y. So it always rescales the points in the input space. And so this can be interpreted as a rescaling, but of the horizontal axis. So let's have a look at what happens if we change these parameters in here. So if I increase the variance of the Gaussian process, I just dilate the samples of the GP, and if I reduce them, I'm just going to collapse it. And if we look at the length scale, if I make the length scale longer, the process is going to be stretched, so less and less wiggly. And if I make the length scale shorter, the process is going to have high frequency variations in it. All right.
Nicola, I've got a couple of questions
about
the positive semi-definite. So one thing is, so is the periodic kernel semi-definite?
Yes, it is. All kernels are positive definites.
And there's been a couple of questions from this session and from the last. Could you have a neural network as a covariance function or a mean function, and how would that affect the positive semi-definiteness?
Yes, so you can have a neural network as a mean function, and people have been using that. You cannot directly have a neural network as a covariance function, because you cannot guarantee using a neural network that the function that you get after training is positive semi-definite. So yes, for neural networks in the mean, not directly for neural networks inside as a kernel function.
Okay, and the previous theorem, is that related to the Carhonen-Loewe transformation related to PCA?
No. Okay. It's a completely different one.
And is the positive semi-definiteness important for the invertibility of the ground measure, or are there other reasons why you need it?
So you can invert a matrix that has negative eigenvalues. So it should be, in a way, the expression we have for the mean and the covariance would still make sense with from a pure mathematical point of view for a matrix that is not positive definite. The only thing you don't want is to have 0 eigenvalues for your matrix, because then you have a degenerate rank and you cannot invert the matrix anymore. But we lose all the meaning we have for the models. So it's not just a technical question that we cannot invert the matrices. It is more fundamental about does it make sense to have something that is negative? And as I was saying before, having a matrix that is not positive definite means in a way you have something in your model that you interpret as a variance, but that is negative, so it doesn't make sense. Or if you look at the RKHS point of view, it means the norm you're using is not a valid norm, or the inner product you're using is not a valid inner product.
And so there's no requirement for it to be stationary. So you can have non-stationary kernels that are positive definite, right?
Yes, like the Brownian motion or splines kernel. Yes.
Okay, I think that's for now, and then I'll ask some more in a bit.
Sure. Okay, so those are a list of covariances. If we look at the way these functions look, so here's an example. So many of them look like a bit of a hat function that take the maximum value when the two variables are equal, and then that decay when you go far away. So this is just saying if you evaluate 2 points that are the covariance for 2 points that are very far away, then there's basically no correlation between these points. So there's no information we can extract from one point for the other. These two variables will be independent if they are very far away, or they will tend to be independent if the 2 points where we evaluate the GP move away one from another. But all functions, all kernel functions don't have this bell shape. This is an example of a periodic kernel. That's another periodic kernel. You can see in here that a kernel can take negative values, for example. So being positive definite doesn't mean that the function itself is positive everywhere. And yeah, so some of them have shape very different than others. And if we look at the samples that are associated to these covariances, we can also see that the samples have very, very different, look very, very different. They can be extremely smooth if we use these covariants. So here you can differentiate the sample as many times as you want, or they can be rougher and rougher if you use different kernel from the Matten family. They can just be constant function if you use a constant kernel. They can be discontinuous everywhere if you just look at the white noise process, or they can be periodic functions, linear, some polynomials, or yeah, other types of shape. So that Gaussian process model have a lot of flexibility because we can, by choosing the mean function and by choosing the covariance function, we can choose very different behavior for the model. I'll detail that later on.
Just to clarify, what are the difference between the cosine and the periodic covariances in terms of modeling periodicity?
Yes. So if you sample from the cosine kernel, your sample will always be an exact sinusoidal wave, just with a phase that can change and an amplitude that can change. But these guys will basically just be exactly a cosine shape. If you sample from a periodic kernel, you have much more flexibility. So you do not constrain the sample to be exactly cosine shaped. They will be periodic, but not exactly with like one frequency. You'll have a mix of different frequencies that will change from one sample to another.
And if variances have to be positive, then how can you have the covariance between 2 points be negative, given that the covariance function can be negative and still be positive definite?
Could you say that again?
If the variances have to be positive,
yes,
then how can you have covariance between 2 points be negative?
Okay. The answer is just you can. When you compute a covariance, it is typically the correlation times the two variances, right? But the variance times the two standard deviation. The standard deviation are positive, but the correlation coefficient can be negative, right? So you can always have points that are negatively correlated, and that leads to negative covariances or negative kernel functions. A simple example is to look at the sample from the linear kernel. If you look at the value of the sample here is going to be exactly the opposite of the value of the sample there, right? Because I've just take straight lines that go through 0. So these two values here and there, they are exactly negatively correlated, right? So the kernel function between here and there is going to be -1. We can look at it in here. The covariance between the point at 1 and the point at -1, well, we can't see it in here, but this would be -1. I hope that answers the question.
Okay, and what if you wanted like you wanted to change the variance of the kernel?
I'll talk about that toward the end of the talk. All right.
Yeah. Thanks.
Okay. So now let's say a few words about Gaussian process regression again. So let's say we have observed a function f at a few locations in space. So for a few input points, we've observed the value f, and we want to have an idea about what's happening outside the points we have observed. So if we want to predict what's happening, for example, at this location, we cannot make any prediction if we don't make an assumption, if we don't make hypothesis about the behavior of what's happening in there. And if you were to ask a human, it would probably say, oh, I guess, I don't know, maybe the value is over there. And if the human says that, is because it can see some like continuity, some regularity in the function that we have sampled. Another guess could be to say, oh, just the pattern I can see here is completely at random, and I don't know what to predict in there, but a human would infer naturally the regularity, and in order to make a prediction about values that have not been observed. And we have to do the exact same thing from a mathematical point of view. We cannot make a model without making assumptions. And of course, you're at the Gaussian process summer school, so it's not a big surprise. The assumptions we are going to use is that the function we've observed comes from, can be approximated by a Gaussian process. Or another way to put it is, the hypothesis we're going to make is that the function we want to approximate is one sample from this infinite set of samples. And now we can combine these two information. So we can combine the data we have and the modeling assumption that we make that our data comes from one of these samples, and we can compute the posterior distribution. And the posterior distribution is still a Gaussian process, and it can be computed analytically. So it has a mean function that writes like this, and a covariance function that writes like that. And as Rich was saying before, the formula we use to write that down are exactly the same formula we derived for the conditioning of a multivariate Gaussian vector. Because if we want to predict what's happening at the point x, for example, in there, we plug a x in here, and then we just end up with a conditional distribution of a multivariate normal, right? So we just plug in the formula we've seen before. So we have the covariance between these two quantities times the inverse of the covariance matrix times the observation, and same thing for the variance. So now we can sample from the posterior process, and that gives us a distribution for every point where we want to make new predictions. And one way to summarize this conditional distribution is just to represent its mean and some confidence intervals around each point where we want to predict. Another way to look at it that I like a lot is if we look at these samples from the Gaussian process, and if we look at the data, one way to combine these two information is to, in all these samples, get rid of all the ones that do not go exactly through the observation points that we have. And if we do this, we will end up with exactly this type of posterior samples. Any question?
One question, what is y in the expression?
Okay, y is the notation I use for the Gaussian process. I can use y or z. So in this plot, I'm saying the Gaussian process at a point x in space, so the x variable in here, given that I've observed at some location x, uppercase x. So this uppercase x is a vector. I have a vector of observation for all these points.
And one of the voted questions is, why do you take random samples when the kernel is already defined?
So I don't, to compute the conditional mean and the conditional variance, I don't need to sample from the process. It's just one way to understand what, when you choose a kernel, you choose some assumptions, and plotting the samples or looking at the samples is one way to understand the assumptions you put into your model. So it is very important to understand this link between the kernel and the samples, because that's what's happening under the hood. When you pick a covariance function, you change the assumptions you feed your model with.
Is there a typo in C of XY?
No.
Okay, yeah, just checking. Somebody's suggested that there is, but
no. So maybe it's because of the the notations I'm using. So maybe I can say a bit more on that. So here we can assume that lowercase x and y are just points in the input space. So this is just a scalar value. X is a vector of the input location of the observations. So this will be a matrix that has one line and n columns. If we have n observations, this is going to be an n by n matrix, and this is going to have n lines and one column. So this expression here is just a scalar. I hope that that clarifies.
Okay, it's yeah.
Okay.
And just a quick question on: is a GP a universal function approximator? Like
yes.
A neural network is. Yeah.
Yes, it is. Okay, so a few remarkable properties from Gaussian process regression models. So the first one is that they can interpolate the data points. So we've seen that previously. Maybe we can look at why this is true. So if I want to predict that one of the point x, uppercase X, I've already observed, this matrix here that has, so if I plug uppercase X in there, this is going to be a matrix times its inverse times the vector of observation. So the predictions I'm going to make are going to be exactly the values I've observed. And similarly, if I do that for the variance, I'm going to find that this is 0. So they can interpolate the data point. If you don't want them to interpolate, we can use observation noise, as Rich was discussing earlier. The prediction variance does not depend on the observations. So here's the prediction variance. If we look at the expression, it does not depend on f. So this is either a bug or a feature of Gaussian process model, but that's one notable fact. The mean predictor does not depend on the variance parameter. So if you remember, the variance parameter was the sigma square that was inside, like as a factor inside the expression of the covariance. If we were to take it out over here and out over there, it would cancel because of the inverse we have here. And the mean usually comes back to 0 when you predict far away from the observation. If the point x is very far away from the observations, and if your covariance function has a hat shape like most of the covariance we've seen so far, then this will tend to 0. So the mean will tend to 0. Let me illustrate that on an example. Let me reload this page. It should just take a second. Okay, so here's an example of a Gaussian process model. So I have 2 observation points in here. The mean of the model is 0, and I have a Matten 5/2 covariance function. So if I increase the variance in here, the confidence intervals are growing bigger and bigger, but the function itself for the mean does not change. There was one thing about predicting far away from the observation. Maybe I'll show this. If you predict far away from the observation, so one way to predict far away from the observation is to have a small is to have a small length scale. So actually, I'm going to come back to this guy. In here, if we want to make a prediction of what's happening here, we do have 2 observation points, but since the Gaussian process is very wiggly, we are very far away when we want from the observation when we want to predict here, and the observation do not have any influence anymore. So the model basically reverts to the prior distribution, right? And if I change the mean of the Gaussian process, so if I change the prior distribution, we can see that the GP just revert to the value of the mean. So the same value as if we had no observation at all in here.
Just a couple of questions on this. If you have a small length scale, is that more likely to lead to overfitting?
Okay, that's a good question. So we usually say that Gaussian process models don't overfit, and this is because they are non-parametric models. So you cannot adjust the model more and more in order to fit just the training data. You will always have the model that will have its own uncertainty, and yeah, we usually don't have issues with overfitting in Gaussian process models.
And what recommendations would you make for extrapolation if you're getting obviously as you move away from the observations, your GP is going to revert to the prior? Are there any tips and tricks for that? A few people are asking in various different ways how to deal with extrapolation.
Yes. So first of all, it's the fact that the model reverts to the prior is a very good thing, and that tells you should make your prior as informative as possible. If you know there's I don't know, a trend in your data, you should definitely include this trend into your prior, so your model will be informative even if you are far away from the observation points. But the great thing is you can check, you can see that your model reverts to your prior. So the model is not wrong in doing so. It's just telling you, I don't have enough data points to make a meaningful prediction at this location, or your data points do not influence my prediction in here.
And just questions on the kind of the hyperparameters. Are hyperparameters independent of each other, or would you put priors on them? And once somebody's asked, you say that uncertainty does not depend on the data, but isn't there implicit dependence through estimation of hyperparameters?
Yeah, that's a good point. So when you estimate the parameter of the model, then of course that will influence in a way it influences the prior, right? So it is going to influence what is happening, and the input location will also influence the uncertainty. Like the uncertainty is smaller close to observations, but the value f just do not appear in the variance. Yeah, but that's a good point. It does influence when you estimate the parameters. Can you repeat the first question, Willa?
Are the length scale and variance independent? And
Yes.
If not, what practical things do you do that? And then someone's just asked that if you're maximizing marginal likelihood, are you not going to get overfitting from optimizing the hyperparameters?
Okay, I'll come back to the overfitting question later on because I have a slide on that. And when it comes to the variance and the length scale parameter, yes, those can be seen as independent parameter. Like one of them rescales the x-axis, the other one rescales the y-axis. So you can tune them completely independently. There is a case to account for the geometry of distribution when you optimize the parameter. And if you're familiar with natural gradient, it makes sense to use natural gradients when you want to optimize the parameter of a model. But yeah, the short answer is they can be treated as completely independent.
Okay, just carry on. I'm going to read through some more questions because they're all coming in now.
Okay. Okay, so we've illustrated these properties. And so why do we like GP models that much? So the first bit is because they are data efficient. So we don't just use the data, we combine the data with some prior information. So this allows us to solve problems with less data. A simple example that I remember was puzzling me when I was studying Gaussian processes a long time ago, is that if I want to compute the mean of a function f, what is the difference between just I take some points and I compute the empirical mean of these 7 points, or I do a GP model and then I compute the mean of samples from the model. And it turns out that the second option is much more accurate, because you account for it's much more accurate if your GP model makes sense, right? If you put the right assumptions, of course. But it is much more accurate because you add to the solution of your problem the information that the function you want to study is smooth. So you will end up with better estimates if you account for this extra information when you want to compute just the mean of the function you want to approximate. So adding information into model is good, and it's a way to, it's a data efficient way to solve problems. The second thing is about uncertainty quantification. So this is another big advantage of Gaussian process model compared to neural networks, is that we have good uncertainty quantification outside the points we have observed. So if you want to compute some risks, so for example, what's the probability for this function to be above 4, let's say. So we can compute this kind of risk, and to do that, you need to know what's the uncertainty on the predictions you're making. Another thing is for some active learning. Javier will be talking about Bayesian optimization on day 3. So you can use this information about what the model knows and what the model doesn't know, because it doesn't have observation in this region, in order to design an algorithm that will help you to minimize a function, for example. And the last point of why we like GPs so much is because they are mathematically tractable. We can do everything in closed form. We don't have to do MCMC or things like that. That's a very important factor. This is true for Gaussian process regression. It's not that true if you have observation models that are not Gaussian, where we don't have closed form expressions. But there are workarounds for this that will be discussed later on during the summer school. And yeah, a few words on the complexity. So in order to compute the posterior mean and covariance, so we need to store covariance matrices. So the storage footprint is quadratic in the number of observations we have. And we have to invert the covariance matrices, or more accurately, to compute the Cholesky factor, apply triangular solves. And this is cubic in the number of observation points. In practice, the complexity that is cubic is something where you have to wait for it, but like if you have time, the computer will do it. The main issue is more about the memory we have on our computers. And this is kind of the boundary we get, like memory errors when we try to manipulate covariance matrices that are too big. So with hardware nowadays, the number of observation points is like typically somewhere between 1,000 to 10,000, sometimes maybe 50,000 if you have a good desktop, or on a very good machine. But yeah, this is for what I've just presented, Gaussian process regression. You can't do with much more than a few 10,000 data points. And if you have more data, there will be a talk from Denhen tomorrow using sparse GPs. A few words about parameter estimation now. So yeah, so the choice of the kernel parameter has a great influence on the model. Let me illustrate that again in here. If I make the covariance the length scale larger, that completely changes the model, right? Or if I change covariance function, it does change the model a lot if you just tweak these parameters. So a very good question is, what should be the values of these parameters? So either you don't have any information at all about it, and we can use maximum likelihood in order to estimate these parameters, or if you have some prior knowledge about these parameters themselves, then you can also build a bigger probabilistic model where the length scale and the variance themselves are random variables, but then you don't have closed form expression for the model mean and for the model predictions in general. So you need to resort to MCMC for example. So I'll focus here on maximum likelihood estimation. So the likelihood of a distribution with a density, so a PDF fx, given some observation, is just the product of the density evaluated at the observations that we have. So if you have some observations that are very unlikely according to the model, then the likelihood is going to be small. So in Gaussian process regression, what usually happens is that we have only one observation from the vector. We have one vector of observation, like this would be just one sample from the distribution, but we can compute this quantity. So what is the likelihood of the observation that we have, and we can maximize, we can pick the kernel parameters, so the variance and the length scale, such that this quantity is as high as possible. So that's one way to learn the kernel parameters directly from the data that we have. And you may wonder, why are we using likelihood? Why does it make sense? And if we apply the chain rule, the likelihood of the vector of observation can be seen as the PDF for the first observation times the PDF of the second observation given the first one, and so on and so forth, the third one given the first two, up to the last one given all others. Right? So what we are saying here is, if you have a high likelihood, it means all the terms in this product are going to be high. So it means that the observation F1 makes the prediction for F2 given F1 is likely. The prediction for F3 given F2 and F1 is likely too. So a high likelihood means basically with a set of observation, you can efficiently predict the next ones. So that's why it is very principled and very well used to use the maximum likelihood to estimate the parameter. It's because if you have a high maximum likelihood, it means you're able to make predictions using a subset of the observation to predict the remaining ones. Maybe I can pause for questions.
Yeah, a couple of questions going back is, I think, could you provide some more intuition between choosing the prior for your mean function and the covariance function? Like one person, if you had a periodic trend that you knew about, yes, would you put that periodicity in the mean or the covariance choice, and how does that choice affect guarantees such as smoothness and differentiability? Okay,
so I personally I'm a big fan of putting as much information as I can into the kernel function, unless you have you're talking to the person who handed the data to you, and they tell you, oh, I know the mean should be, I know they are centered around these values, or I know this is a very good estimate for the data because of some physical reasons. Then I would definitely use this and plug it into the model as a mean. But another way is to have a parametric model for the mean, like a linear regression model or a neural network. But in a way, I find it a bit weird we have a non-parametric model and we include into it a parametric components. And you can include everything into the covariance function, unless you have some very clear information that I know it should be centered around this value, or I want to approximate this expensive numerical simulator, but I have a very cheap numerical simulator that gives me a very good indicator of what the value should be. So if someone gives me this problem, I'll use the cheap numerical simulator as the mean function of the Gaussian process model that approximates the expensive one, because there's information in there I can reuse in my model. But other than this type of situations, I would tend to put everything into the covariance function.
Thanks. And then just a couple of questions on maximum likelihood. So somebody's asked, is maximum likelihood the same as... Oh, I've lost the question, just a sec. This Sim Q&A is not great. Okay, while I find that, sorry. One of the questions about maximum likelihood, if the likelihood's low, will maximum likelihood still work?
Yes. Yeah, I would still use it. It is an indication that maybe your model isn't great, and maybe you should consider other main function, other kernels, or other hypotheses into your model in order to make the likelihood higher, right? You can definitely use the likelihood to compare different models, provided that they have a similar number of parameters.
Thanks. And the question was maximum likelihood and maximum marginal likelihood. Are they the same?
Yes. Okay, I'll keep going. So now we've seen how to build model. So we get data, then we fit some parameters, and we can make some predictions. But it's very important to make sure that the model we have in hand makes sense. So the typical thing to do is to introduce some new data, some test data, and to compare the model prediction with the reality. So here's an example. I fitted the model on the black cross, and I have some extra data that is given by the red ones. So ideally, we like to check a few things. So of course, we want to check that the prediction of the mean of the model are accurate. So a typical example a typical criterion used for that is to compute the sum of the square distance between the mean of the model and the actual observation. So that just computing mean square error is a good check. The model also provides their own measure of their confidence, so we should check that too. Simple criterion could be what's the percentage of points that end up in the 95% confidence intervals. So we would like this percentage of point to be around 90, obviously, but that can give you an insight if the model is too overconfident or underconfident about the predictions it's making. And another interesting thing is the model also predicts the covariance between test points. So it's something that can be checked. So according to the model, the observation at the test points, they are normally distributed, and they have this mean and they have this covariance matrix. So if we take our vector of observation and we subtract its means and we multiply by the inverse of the Cholesky of the predicted covariance, this results in a vector where all the components should be n01 and independent. So we can check that. We can plot an histogram of basically this vector and compare it to a standard normal variable and see if this makes sense. If I obtain this type of plot or this type of quantile plot, I'm very happy to proceed with my model. So those are the one I obtained for this graph. So the model is not extremely confident about the prediction it's making, but if we look at the test data we have, it's saying that there is indeed some variations outside, like we can depart from the mean quite a lot, and this is accurately captured by the confidence interval. So this is basically what we are saying here. The model is not underconfident or overconfident. And so I'm very happy if I see this kind of validation plot. Most of the time we use Gaussian process model because we don't have that much data. So we use them because they are data efficient and data is expensive to collect in many cases. So a classic thing is to apply leave one out. So the idea is to build a model on all observations except one, to compute the error at this point, and then to iterate again and again, excluding a different point each time. So let's say this is the model we want to test. We can remove the first observation point, look at the prediction of the model, and then compute as before what's the distance to the mean, is the point inside or outside the confidence intervals. When people do that, there are basically two philosophies. Some people will fix the model parameters each time they remove one point in here, so they will always test with the same model parameters, and other people will refit the model each time in order to integrate over the variability that comes from estimating the parameters. Both of them are valid things to do, just they are not testing the same thing. And so as before, we can compute mean square error, or we can compute the standardized residuals and see if it makes sense. Okay, any question on model validation?
Not so much that you haven't already answered.
Okay.
A couple of clarifications though. So the modular kxx function in the maximum likelihood term, does that act as a regularization term? Having the covariance function in there.
Do you mean the denominator in here?
Yes, I think so. I think so. Yeah.
Yes, this denominator here will favor, in a way, simpler models, so models that are picked around the data that you have, and the term will penalize models that put mass more or less everywhere. So if you think about, you have a bunch of observation and you look at the maximum likelihood coming from white noise, the maximum likelihood actually is not going to depend on the location of the points, right? Regardless where the points are, this will always be a diagonal matrix, and this will always be a diagonal matrix. So this will not influence the model. So the location of the points does not affect the maximum likelihood estimate if you have a white noise kernel. But if you can find a simpler, because the white noise kernel is going to put basically mass everywhere. But if you have a simpler function, so a function that has some correlation, it will make this term lower, this determinant will be smaller, and the model will naturally favor a model that have more regularity, and not like that much model that are pure white noise. It's thanks to this term here.
Thanks. And just a thing about the scaling. If you've got multiple dimension input,
yes,
how does that affect the kind of limitation with scaling the number of data points? And would it be sensible, plausible to have different priors in different input dimensions?
Very good question. So all the complexity we've seen so far, they don't depend on the dimension of the input space. They just depend on the number of observations. So that's a very good thing for Gaussian process model. If you have more than one dimension, you can have length scale parameter that are different for every input variable. So remember, the length scale is a rescaling of the axis, and you can choose to rescale differently the various axes. So you may have more parameters to your model in higher dimensions than you have in one dimension.
Thanks.
Okay, so choosing the covariance function. So sorry, Rich, I'm using Gaussian kernel in here. I really mean squared exponential, or RBF, or exponentiated quadratic. So these two models are with the exact same data, but the predictions we make are completely different. And there's no model that is better or worse than the other. It's just model that correspond to different assumptions, a different behavior of the phenomenon that generated the data. So we should choose the covariance accordingly to the belief we have on the function. So it's very good to talk to practitioners when they give you data to ask them as many questions as you can in order to get an insight on what's the phenomenon behind. Is it something that is smooth? Is it something that has some periodicity? Is it, all these questions are very interesting in order to make the prior more informative and to end up with a better model. So the kind of questions you can ask to the practitioner is it stationary? So they may tell you, oh, I know the variability in this area of the space is bigger than in this area, these kind of questions. Most of the time it's difficult to explain why it is non-stationary or to give the exact feature of the non-stationarity. So it's also common just to use a stationary covariance function, even if we know the phenomenon may not be stationary. If it's differentiable, what's the regularity? Do we expect particular trends? If there's some particular trends, of course, we want to put them into the mean of the model. And do we have some specific patterns like periodicity, cycles, or a combination of high frequency and low frequency variations? Something that is additive if you have several input variables, these kind of things. All this information can be included into the models. And as Rich was saying earlier, the common practice is trial and error. So to try different covariances, to try to make them as informative as possible. And yeah, and the thing that is also very, very good is to try some input or output remapping, so to try to change the variable like that. This can help to make the data more, the process more stationary when it is not. So that's another way to, yeah, to make the model more informative, to make the assumptions we make better fitted to the data. Sometimes it's just to modify the data a bit in order to match our assumptions. So we've seen previously that there's an equivalence between being a covariance of a Gaussian process and being a positive semi-definite function. So for a few covariances, we can prove that directly from the definitions. For example, if you look at the white noise kernel or the constant kernel, we can use directly the definition. But for many covariances, it's not that straightforward. So there's a very interesting results that is just for stationary covariance functions, is that if a function is stationary, so we can write it just as a function of one variable, that is the distance between the two, it will be positive semi-definite if it is the Fourier transform of a positive measure. So this is very convenient for us because we've changed the condition of being positive semi-definite into the condition that this just has to be positive. So this is just a function that has to be greater than 0. This is much simpler than saying the covariance matrix coming from this has to be positive semi-definite regardless what are the input points where we evaluate it. So this is very convenient, and we can use that to generate a covariance function or just to check that covariance functions that we are using are positive definite. So here's an example. So we consider a measure that is just a step function. If we take the Fourier transform of this, we end up with a sinc function. And according to Bochner theorem, since this is positive, this can be used as a covariance. So if we look at usual covariances, so the RBF kernel is the Fourier transform of itself. So, and itself is a positive function, so it is positive semi-definite. And math and kernel are Fourier transform of measures that write like this. So they also are positive semi-definite. And there will be a talk from Andrew Wilson this afternoon. He will not be talking about that, but this is some interesting work he's done a few years ago already, where you parameterize a covariance function in the spectral domain. So you just say my covariance function is going to be the Fourier transform of a sum of Gaussians that are parameterized by their mean and their standard deviation. And since this quantity, since this measure is positive, we know we can use it as a covariance. Just one thing, this is symmetrized around 0. This is just to ensure that the GP we end up with is real valued. It doesn't have to be symmetric, but then you'll end up with complex covariances and complex samples. So yeah, we can use Buckner theorem to parameterize a Gaussian process by its spectrum. And if we look at some sample path from the previous covariance, this is how they look. So they are not exactly periodic, but they are wavy. They are wiggly. And if we look at the covariance, so I don't have the y-axis, but this is the value 0. So you can see there's a negative covariance between points that are kind of like half a period apart, and then a positive covariance again when you are kind of 1 period apart. But if you are far away, you just have no correlation at all. So you can completely be out of phase between 2 points that are far away. So this is where you observe this kind of wiggly behavior, but it's really not periodicity because it can completely go out of phase. So if you want, I don't know, to model the waves coming or waves on the ocean, then I guess like this covariance function is something that could make sense. It's not perfectly periodic because we know waves are not, but there is some quasi-periodicity in there. So now I'm going to talk how to define new covariance functions. And a very common thing is to take existing one and to modify them by combining them together. So kernels can be summed together. Either you sum kernels that depend on the same variables, or you pick kernels that depend on different variables, and you sum them together to make a function over the joint input space. Or you can multiply kernels together, or you can compose kernels with a function. And all of these operations will preserve the positive definiteness. So let's see how this can be useful. So here's an example where I pick 2 covariants, a math and 1/2 and a linear kernel. And when I sum them, I obtain this new covariance. And I know I can use that in GP models. If I look at what it means from the modeling point of view, it means basically I have one GP that has the Matten covariance, another GP that has a linear covariance. I just sum these 2 GPs. So you can think of that as just summing the samples of the GPs, and we end up with something like that. So basically, there's no way to see a difference between sampling from the sum of the covariances or sampling independently from the 2 covariances and summing the 2 samples together. This will end up in the same thing. So if someone tells you, oh, I believe there's a linear trend, I don't really know what the coefficient is, but there will be some variations around the trend, then you can definitely choose this as your covariance for your model. Let's see how this can be useful. So that's an example from the Gaussian process for machine learning book. So that's a data set that has the monthly concentration of CO2 in the atmosphere. This is measured in Hawaii in an observatory, at the Mauna Loa Observatory. So here it is represented as a function, but if I were to zoom on that, that would just be like monthly or weekly points over 50 years. So if we try to use squared exponential kernel and to make a predictions, we can either say, oh, I can see some high frequency variations in here, so I'm going to pick a small length scale to represent these variations, but then the model is very bad because as soon as you try to predict a bit into the future, the model drops back to the mean because it says, oh, I'm too far from the observation to predict something meaningful. So here the uncertainty is kind of good, but the mean prediction is very bad. And on the other hand, you can say, oh, I can see a general trend that is the CO2 concentration is increasing. So I can use a large length scale in here and fit a GP model. And now the mean is better, but the confidence intervals are completely wrong, just because they do not. We sure, right? A human would know that the next samples are not going to be in there. But now, what happens if we sum the two covariances? We say, oh, I know I have two components into my signal. I have a low frequency variation for the trend, the high frequency variation for what's happening on the yearly basis. And then we end up with this model that is much, much better. Now both the mean and the confidence intervals make sense. And actually, if we look at more closely at the data, we can see some periodicities because the CO2 concentration is higher during summer and lower during winter. So there's exactly a 1 year period. So we can tell the model that you should expect some periodic behavior in here. And unfortunately, I can see a trend, and it seems to make sense to have a quadratic trend in the model, but I can include this trend into the kernel too. And we can use maximum likelihood to estimate all of the parameters in this model, and this is the kind of prediction that we observe. So that's now a very, very good model. Just because we have the right construction block into the model, we put the right assumptions about low frequency variation, high frequency variations with large and small length scale, plus periodicity, plus a behavior that will be quadratic if we want to predict very far away from the data points. Any question on this?
There was one about would it be better to offset this with a linear trend and then fit?
You can do it. That would be exactly equivalent to fitting your linear trend and then adding it to the model as a mean function. There's no difference from a GP point of view. The thing that I like when putting the trend or the quadratic trend here into the covariance is that in a way it is penalized. So if I were to put a very, very large value for this parameter, I would end up with exactly the same thing as fitting the model first and then applying GPA regression on top of it. But here there's some like penalty associated with it that goes through this parameter. But they are, with large value of this parameter, the two approaches are exactly the same between having the trend inside the kernel or the trends inside the mean.
How do you distinguish between the low and high frequency RBFs? Do you initialize the parameters differently during optimization, or do you just expect them to automatically find those two trends independently?
Yeah, it's a very good question. So the better you initialize the model, the faster the optimization will be, but also you're less likely to end up in local minimum when you optimize them. So in this example, I indeed handpicked high frequency, low length scale for the high frequency and the large length scale for the low frequency variations. If you initialize them with the exact same value, I guess you'll have a numerical issue that you don't have gradients to differentiate the two of them. So it's better to initialize them the best you can, or at least at random, but not at the same location.
Yeah, and how would you know whether to add the covariances to build this, or whether you should multiply kernels?
Okay, in this, so we can come back to what's happening from the sample point of view. Does it make sense to say here that I can decompose the signal in a sum of signal, one of them being low frequency, the other one being high frequency? Yes, I think so. So if I believe the signal can be decomposed as a sum, then I want my covariance to be a sum. All right, I'm going to talk about the product in the next slide.
Okay, yeah, that's fine. I think some of this can be, yeah, there'll be questions that I'll ask later.
Okay. Okay, so before we were summing kernels that were depending on the same inputs. Now we can sum kernels that depend on different inputs. Let's say we have variable a dimension 1 and a dimension 2. We can have covariance over the first dimension, another covariance over the second dimension, and then we sum these two together. And from a GP point of view, this will can just be interpreted as the covariance of the sum of a GP in the first direction and a GP in the other direction. So if we look at samples from this, we can see the samples are additive. So those are great if you want to approximate additive functions, because you're providing your model with a lot of information by saying that it should be constrained to model only additive functions. So there's plenty of behaviors that you can't see with this data because I know it is additive, so I'm giving you an additive covariance function. Or if you want to build a model over high dimensional input spaces, generalized additive models are very well known and very used for high dimensional data. So that's one way to end up with additive models. That's the way to end up with additive models with Gaussian processes. Yeah, so if we look at the posterior mean, so this is the exact same expression as before, just I'm writing, I can expand this first term as this sum. So this can be interpreted as the conditional expectation, and this is another conditional expectation. If we look at them in details, M1 here is basically predicting the GP that is on the first variable, given that I observe the GP on the first variable corrupted by the variations by the GP on the second variable. So this is like a GP model with observation noise, just the observation noise is structured, it is correlated by what's happening on the other direction. But in a nutshell, the mean function will be a function of x1 plus a function of x2. So it's still an additive function. If we look at the prediction variance, it has some interesting features. So if we just use a classic covariance, we'll have a zero variance. So these plots are control line of the variance of the model. So we have two inputs, some input locations in here for the observations, and the control line of the variance. So if we move away from the observation, the variance will increase and will plateau at the prior variance. But the behavior is very different if we use a sum of kernel. So here, for example, we can see a low variance even if we don't have observations in there. And this is because having an observation here, here, and there, and with the assumption that the function is additive, basically tells you that we know the value here. The value here is going to be this value plus this one minus this one. So the model, even if it doesn't directly have an observation, it knows what's happening because it has the right data and it knows the function has to be additive. So this can be used to in higher dimension to get models that are quite accurate, even with a number of points that is just grows linearly with the dimension. So here, if I just have observations along the axis, I'm going to have a prediction variance that is 0 at all these points on the grid. So that's why additive models are good in high dimension, because they don't need that many observations. And they can still be used if the function you want to approximate isn't additive. Sometimes it's reasonable to say that there's some component in the signal that is additive plus something that departs from it. But at least if you're in high dimension and you don't have that many observation points, the best you can do is just to learn the additive parts of your function. So it still makes sense to use additive model even if your function is not purely additive. Okay, product of covariances. So we can make the product of two covariances. This is still valid. That's an example where we make a quasi-periodic function by multiplying a cosine kernel by a squared exponential. We can also make product over for kernel that are defined over different input spaces. It turns out that for the squared exponential, we recover exactly the two-dimensional squared exponential kernel. And another thing is we can compose a kernel with a function. So if K1 is a kernel over D1 over a space, and F is a function that maps D to D1, then we can basically remap the input to the function F. This will still be a valid covariance function. And basically, this can be seen as a rescaling of the input that is nonlinear. So when we introduce length scale, we're just dividing the input location by theta. This is a bit more convoluted. We do not just divide by theta. We introduce a rewarping of the inputs. And yeah, so here's an example where the rewarping is 1 over x. So basically, we just like compress the space a lot in this. So we have high frequency variations in there, and then the samples becomes more and less wiggly when we move away from 0. And if we look at the kernel, the kernel is non-stationary anymore. It changes depending on where you are in the input space. So it's kind of having a small length scale around 0 and larger length scale when you move away from 0. And yes, and of course, all these combinations can be combined. So for example, this expression is a valid kernel. Why that? So because we know that the linear kernel is x times y, right? So this is a linear kernel, but that is remapped through where the input is remapped through the function f. So fx times fy is a valid covariance function, and then we multiply it by another valid covariance function. So this is a valid kernel. And now we have a covariance that is like this, that is non-stationary, where the variance is high towards 0 and small when you move away from 0. So this is one way to encode like non-stationary variance, just by multiplying by a function here that will inflate or deflate the variance depending on where you are in the input space. And can we automate the construction of the covariance? Yes, there are some works on that. The most famous one being the automatic statistician. So the idea is to consider a set of possible kernel functions and a set of possible combinations of kernels. So as we've just seen, we can sum covariances, multiply them together, or we can introduce change points. So it's basically in one dimension, it's one location in the input space where you use a covariance on the left and you transition to another covariance on the right of the point. And yes, and then it will build a graph of starting from a simple covariance and trying to make the covariance more and more complicated by using these operations. And then it uses a greedy approach to find the kernel that minimizes this quantity. So as before, we are trying to maximize the log likelihood, but we also introduce a penalty on the number of parameters that we have inside the model. If you make a model more complex by adding a covariance, your likelihood will, after estimating the likelihood, it should always be higher, because you can typically turn off by choosing a 0 variance for the point you add, so it can only be better. So using a BIC is one way to have a penalty on more complex model in order to, in a way, avoid, I don't want to say avoid overfitting, because TP models don't really overfit, but yeah, avoid over complex models. Any questions before the conclusion?
What if you had multidimensional observations? How would that affect the construction of the covariance function?
Yeah, great point. So you can have kernels that are for multivariate outputs. There's a very good review paper from Mauricio. I would encourage you to read it if you want to work on multidimensional GPs. But yeah, that can definitely be integrated inside the covariance. So just your covariance doesn't just output a single scalar value when you compute the covariance between 2 points. It will output a covariance matrix that describes the joint distribution between all your outputs.
Thanks. And so you said something about the automatic statistician generating human readable reports. What do you mean by that?
Okay, so it's, if we think again about the Munaloa example I was using before, if you just look at the covariance function that will be estimated by the automatic statistician procedure, so they will end up with one covariance function, And then just by looking at the covariance function, you can say a lot of things about the data. You can say, for example, we've seen there's a low frequency variation and a high frequency variations. We can also say there's some periodicity in the data. And that's what the automatic statistician does. It looks at the covariance function and then explains in plain English what are the features that you have in the data. So it will say, I don't know, maybe like 30% of the variance in your data set can be explained by a periodic component that has a 1 year period and things like that. Or there is a trend in your data, all these kind of things. Just by, in a way, analyzing the covariance function and reading out loud what it means.
Great, thanks. And some of the commenters have drawn comparisons with where you're encoding kind of high and low frequency trends in, for example, the more and lower data. This is the kind of comparison with like filtering theory, particularly Kalman filters, where you can encode those trends. Could you just comment on the comparisons between stuff like the Kalman filter and GP regression?
Yes. So when you say GP regression, it does encapsulate a lot of models, and the models that are behind the Kalman filter algorithm can be understood as Gaussian process models too. So there's no difference. Just Kalman filter is one way to do the computation efficiently if you have some Markov property you can use inside your GP. But yeah, it is what I said is very, very similar to Kalman filter algorithm.
When you're designing the kernels and you've got hyperparameters, can you have those hyperparameters as functions of the input as well? So, for example, if you had an RBF kernel and you have the length scale as a function of x to have kind of variable length scale per thing, would that deal with non-stationarity, for example, or?
So this is a bit what I was touching upon when I was introducing the nonlinear rescaling, when I was evaluating a kernel at f of x, f of y. You cannot directly make the length scale a parameter of x because that will not result in valid covariance function, but you can remap the input space in a non-linear way. So this can be understood as length scale that changes over the input space, but it's not directly making theta a function of x. It's applying a function to x. And this function can depend on some parameter that you estimate if you want, right? You can add parameters to you can parameterize this nonlinear remapping.
Okay, great. And I guess there's one big question, which maybe you can answer after you summarize, but I've combined it into one is, if you're starting from scratch and you've got your data, what would you say was a good kind of process to take to design your covariance function, particularly, for example, if you don't know much about the data, how do you initialize the parameters sensibly? Can you integrate known physics into the covariance? And how would you then deal with problems like bad conditioning?
Okay, I'll move to the conclusion because I'm talking about that in the conclusion. Okay, so that's exactly the question that was asked. What are the various steps for building a Gaussian process regression model? So the first one is you will get some data, or sometimes you get yourself to pick the data you get. So the kind of questions you want to ask is, what's your overall evaluation budget? Like how many data points can you query on the system you're working with? What's the cost associated to that? You may want to save some budget for validation and a test set. Another good question to ask early on is, what is your model for? If you want to build a model to do some optimization, then you should save some of your budget to refine the knowledge you have in the regions that seem promising in the input space. So think about what you want to achieve and what's the best way to collect the data. If someone gives you the data, ask as many questions as you can. So for example, if biologists can give you a physical model that is a linear differential equation, you will be able to design a covariance that encapsulates this behavior that you have given by the physical model that is given by the differential equation. So the more information you can get, the more precise you can make your model, the more informative you can make the model. Then you choose a covariance. So this is by talking with the people who generated the data to grab as much knowledge as you can. This is by trying different ones, trial and error again and again on the validation set to understand what's happening. And yeah, so loop over these steps, estimate the parameters. So either doing a maximum likelihood or cross validation. It's a very good practice to do some multi-starts. So you can start with a random initialization of the parameters, and you apply some gradient descent. You will end up somewhere, but you start this optimization again and again, maybe 10 times, maybe 100 times, just to get an idea of what's the landscape of the function you want to approximate. If all your optimizers end up in the same point, you can be quite confident that it's a good thing to do. If they all end up in quite different points, it means that maybe a maximum likelihood is not that. If they end up in different points that have a comparable maximum likelihood, so maybe it means you should integrate over your hyperparameters and not just pick one good estimate, because you have plenty of valid good estimates. And if you just spot like local optimum and one very strong global optimum, then maybe you're good to go with using this optimum. And yeah, and then validate the model on the test set, or doing a leave one out just to make the most of just to make sure the model makes sense and you cannot improve it. So iterate over the step 2, 3, and 4. And in practice, these kind of errors may appear. So errors with a Cholesky decomposition that fail, or matrices that are not positive definite. So those are unless your covariance function is wrong, like there's a problem, there's a bug in it, these errors of Cholesky and matrix not being positive definite are just numerical errors. On the paper, we should not have them, but in practice, we can get them. And this is typically because some observation points are close by. So this is true if the samples are very regular, very smooth. So for example, if they come from the squared exponential, you can have very, very highly correlated points. So that's not good for the conditioning of the matrix. Or if the length scale parameter are very large, it will look like your points are close by, and the matrix will tend to be singular. So one way to do that is to add some very small observation noise, or to impose a maximum bound on the length scale, a minimal bound for the noise variance, or using a covariance that is not as regular as the RBF is also a good practice. And I think that's all I wanted to say. Yes.
Thanks, David. I think a lot of the questions now are very kind of specific for specific applications. So I think I'd encourage anybody with questions on very specific problems to go to the roundtable and discuss. I've summarized as best I can, and I think now it's probably specific interests. On the practical level, you can come to the labs and ask how we deal with things, and if there's specific questions, obviously you've got the roundtables for Rich and Nicola.
Great, thank you very much. I'm looking forward to the
roundtable
this afternoon.
Thank you, Nicholas. Thank you, Will. So we're gonna break now for lunch, and we're gonna be back at 2:15 for the lab session, and at 2 for the roundtables. So you should have access to the links to connect to those. They're gonna be meetings, so you will have more flexibility to ask questions. It will be a more informal sort of setting than the one we have been using so far. So please connect, and if you have time, try to engage with other participants through the Wooba app. And yeah, see you later then.